And welcome back to the second day of this online workshop. So today the first talk will be by Professor Ajith from ICTS in Bangalore, and he will be talking about probes of strong gravity using LIGO and Virgo. So questions I think will be at the end. Otherwise, Professor Ajith will mention during the talk if you would like to take questions. So I will now
I'm happy to take questions during the talk as well.
Okay. So I will now hand it over to Professor Ajith for the talk. Yeah.
Okay, thank you very much, Shumantov. And I wanted to start by thanking the organizers for this kind invitation to speak to you today. I hope all of you are keeping safe. We have had some really excellent lectures from some of the top theorists in this field. So I thought I would focus my talk on the observational aspects of probing this strong gravity using gravitational wave observations, in particular by LIGO and Virgo. So let me just start with just one quick intro slide. We know that GR has been tested very well in a variety of astronomical and laboratory experiments. But as all of you know, gravitational waves offer a probe to test gravity in regimes that are not usually accessible by typical astronomical observations and laboratory tests. Here is one nice schematic parameter space of that various tests of GR probe the nature of gravity. So this is a plot from Nico Eunice's review article. So the x-axis shows the gravitational potential, and by virtue of the virial theorem, it is also the square of the velocity of typical velocities of systems, going from very small values on the left and going to close to speed of light on the right. And the vertical axis is the curvature scale of the objects that are being probed, from small in the bottom to larger in the top. So there are you can basically place all kinds of tests of gravity in this plot. And as you can see, the gravitational waves by LIGO probes certainly extremely relativistic objects. During the last stages of the inspiral, the compact objects move with speeds close to the speed of light. That is the extremely relativistic regime. And also by virtue of the fact that these are probing fairly light black holes, several times the mass of the sun, the curvature scale is also quite large. So in some sense, the gravitational wave observations by LIGO and Virgo kind of span the extremes in this particular way of looking at this picture. And let me also say that the fact that we have observed gravitational waves that are broadly consistent with the predictions of Einstein theory already provides a strong confidence in the description of GR in the regime of to describe gravity in the regime of extreme velocities and extreme fields. So since I will be focusing mostly on the observational probes and trying to summarize the current constraints on various probes, as well as give you a glimpse of the future prospects, let me give you a very short primer on the statistical inference that I would be quoting excessively. As all of you know, there are two major sort of philosophies to draw inference from data, statistical inference from data. Until most of the last century, the frequentist approach was the most preferred one. And here, the idea is to compute a particular detection statistic from the data that describes some measure of the strength of the signal that you're looking in the data. And if you get a number, you can ask, how often can noise produce a value that you got? And that is something like a p-value or false alarm probability in this context. So that is basically, you can ask, if you are able to compute a distribution of this statistic under the null hypothesis, under the absence of signal in the data, then and that is shown by this this little equation. It is a conditional distribution of the statistic under null hypothesis. You can ask, what is the probability that the noise can produce a value like the observed value? So here is an example from real life. The right plot shows the estimation of the significance of the very first gravitational wave detection. So the horizontal axis here is the detection statistic, which is something like a signal to noise ratio. And the y-axis is a number of events. It's like an unnormalized probability density. And these two histograms, let's forget about the difference between two black histograms and the purple histogram, but let's look at one such histogram, let's say the purple histogram. It is a distribution of the test statistic, which is the signal to noise ratio, derived from pure noise, or the background distribution of the test statistic. And you can see that it is very, very unlikely that the detection statistic gets values larger than, say, 12 or 14 purely from noise. And you can quantify it by integrating this histogram from values above your threshold value, let's say 12 or 8. And that gives you a false alarm probability. And the fact that there is one orange square that is, which has a very large detection statistics, tells you that the probability of the noise producing a value like that is very, very small. In this case, it is not even possible to estimate it. It's so small that you cannot estimate it. You can only put an upper bound on the p-value or the false alarm probability. And if you want to write this in terms of, it's of the order of 10 to the minus 6 or so, and in terms of Gaussian standard deviation, it's more than 5 sigma. So that was one way of inferring presence of signals in data. Recently, Bayesian inference, which is much older than, in fact, Bayesian way of looking at the data, has become more popular, because in some sense it is much more natural to use in the quest of scientific knowledge, because we do have a lot of prior knowledge on various hypotheses that we get from other experiments. And if you have a way of, and the science works in way of folding that prior in the upcoming quest or the next quest of knowledge. So there are two ways of looking at making Bayesian inference from the data. One is that you can do a Bayesian parameter estimation. If you have an hypothesis or a model of a signal that describes the signal in the data, you can, under the assumption of this particular model, you can estimate the posterior distribution of the parameters given the data and the hypothesis. So this is naturally following from the Bayes rule or the Bayes theorem. So you can write, so here your hypothesis could be, for example, the GR is correct, H. And then there are a number of parameters that describes the signal in the data. For example, in the case of a binary system of compact objects, the signal is described by the two masses, the spin vectors of the black holes, the location of the binary black hole in the sky, and its orientation, etc., and the time of arrival, etc. So there are a bunch of parameters that describes the signal in the data, which are related to the source as well as its position in the universe. And given the data D, and the hypothesis, you can estimate the posterior distribution of this parameter set theta, and this is given by the product of the prior distribution of these parameters times what is called the likelihood, which is the probability of observing the data under the hypothesis H and a particular choice of parameter theta. And in this case, since the posterior distribution is a probability distribution, it has to be normalized to 1. So you have a normalization constant in the denominator, which is basically called the marginal likelihood, which is, I'll come to that in a second. In this case, in this particular context of Bayesian parameter estimation, this is just a normalization constant. And although you have your parameter space that you want to search for is a large dimension, like 15 dimensions, including the intrinsic parameters of the binary system, as well as the extrinsic parameters that describes the location of the binary in the universe, as well as its relative orientation, the detector, etc. Often we are interested in a subset of these parameters. So you can marginalize your posterior distribution over all other parameters and look at the marginalized distribution of the parameters of interest to you. So in this case, I show a plot of the posterior distribution of the masses of the two black holes in a binary system, derived from the first few binary black hole observations by LIGO. You can also use a different hypothesis to infer parameters. So Arun talked about this, the way of, if you have a different way of writing the waveform, which are sort of, slightly model agnostic. You treat these post-Newtonian parameters describe the waveform as basically free parameters. Then that's another hypothesis that you can think of. And under this hypothesis, you can also estimate the parameters of that hypothesis. For example, the various post-Newtonian coefficients, and then you can estimate its posterior. Of course, Kanchiam Date asked this question yesterday, that these parameters could be completely degenerate with the intrinsic parameter system. So what you need to do is you have to treat, you have to introduce extra parameters in addition to the parameters that you have in GR, and constrain the extra parameters. And in the limit of these extra parameters tending to 0, you recover the GR waveform. That is the way the parameterized tests are done in LIGO. Another way of doing inference from the data using Bayesian philosophy is, if we have competing hypotheses describing the signal in the data, you can calculate the posterior probabilities of the two hypotheses and rank them in order of evidence. So you can again write this posterior. Suppose you have two hypotheses here. One is that GR is correct, that is the HGR, and another is that if you have a given, if you have a prediction of the gravitational wave signal from a given alternative theory, say called H-alt, then you can calculate the posterior probabilities of the two different hypotheses from the data. And this again can be written using Bayes' rule as the product of the ratios of the prior odds, the ratios of our prior probabilities of the validity of these two hypotheses times the likelihood ratios, which are the marginalized likelihood that I wrote in the previous sentence, in the previous slide, in the denominator. So this marginalized likelihood is basically, you write down the likelihood of various parameters in the data, and you marginalize over the parameters of the hypothesis. And that is shown in this this arrow shows how you can marginalize the hypothesis over the parameters of this hypothesis. You basically write down this as a product of the prior probabilities of these parameters times the likelihood of these parameters, and integrate this over. And here, for example, we know that GR has been tested in a variety of astronomical observations and laboratory tests. So we have a very high confidence in GR. So in this sense, the prior odds for an alternative theory is extremely small. This is very, very less than 1. So if you want to claim an evidence that there is an evidence of alternative theory being right in the data, then your likelihood ratio has to be so large so that to offset the prior probability that you have acquired from other observations. So that's why it means that I think Carl Sagan said that unusual observations require unusual evidence, something like that. So it's basically that is a mathematical way of writing the same statement. So that was my quick primer. Okay. So now I want to stress that if we have a model of gravitational waveforms from a specific alternative theory, the simplest and the most intuitive way of deriving inference from the data is that just compute the odds ratio between two models. So we will be done, if you have a prediction of a gravitational waveform from a specific alternative theory. But unfortunately, as we heard from many talks, the field equations of many alternative theories are not very well posed. And it was not quite possible to calculate complete gravitational waveforms from many relevant alternative theories so far in the context of the Inspiral-merger-ringdown of compact objects. So in the absence of specific predictions of the full gravitational waves for the inspiral and the merger of compact binaries, we have to resort to some kind of less satisfactory way of deriving inference from the data. Let me try to get these videos out of my way. Okay. So in the absence of reliable predictions from many alternative theories, reliable and robust predictions, and this is a field that is being changed, so I'm just talking about the current status. The current philosophy is to test the degree of consistency of the data with GR, as well as black holes in GR. So there are, people have come up with different ways of testing the consistency of the data with predictions of GR and black holes in GR. So there are ways of completely model-agnostic signal consistency tests, tests of gravitational wave generation and propagation through parameterized deviations from GR waveforms. One could, in principle, test the nature of gravitational wave polarizations because GR makes specific predictions on the nature of gravitational polarizations. There are proposed probes of horizons or the lack of horizons, as we have heard from Vito Cardoso's talk yesterday. So let me give you a summary of some of the tests that have been carried out by from the data of LIGO and Virgo over the past few years. So the most model-agnostic test, model in the sense of alternative to GR, that you can think of is the following. You can subtract the best fit GR template from the data, and if GR is a good description of the signal in the data, the residual after subtracting the GR template has to be consistent with noise. So this is this shows such a test performed on the binary black hole events during the first two observing runs of LIGO. So what you have done here is to subtract for each event, for example, the 150914, this very first binary black hole event, you subtract the best fit GR generated in the data, and you compute a measure of the signal to noise ratio of the residual data. So you expect the signal noise ratio to be very small, but it won't be zero because the signal noise ratio, the estimate of the signal noise ratio is also a random variable which has an expected distribution. And you can calculate the expected distribution of this residual signal noise ratio from off-source data, where we know that there is no signal. And you can look at several segments of the data and calculate the signal noise ratio from many such off-source segments and look at the distribution of that SNR. And that is shown by these different traces. And for example, this is a background distribution that you expect from this particular GW150914 event. And the value of the signal noise ratio that you get from this particular on-source data is shown by the blue plus. And you can ask the question, how often can noise mimic a value like this? Can noise produce a value like this? And that is of the order of 30% or something. So that is the p-value. So basically you reject this, you can reject the null hypothesis, the fact that there is no signal in the data, only with a very high false alarm probability. So the summary is that there is no significant evidence that the residual contain any signal. And you can repeat this for all events, and so far we do not see any significant evidence of residual power after subtracting the best fit template. Another test that you can do is another signal consistency test, is that if you observe a gravitational wave signal from the entire inspiral and the subsequent merger and the quasi-normal mode oscillations, the ring down of the remnant black hole, you can split the data into two parts. One part is the data signal produced by the inspiral of the two black holes before they merge. There is a cartoon that shows here. And another part is produced by the merger of the two black holes and subsequent oscillations of the remnant black hole. And you can estimate the parameters of the binary from the inspiral part of the data. So you get some posterior distributions of the various parameters that describe the binary under Bayesian inference. Then you can use numerical relativity simulations to predict the final state, because given the initial parameters of binary, the masses and the spins of the black holes, etc., you can predict the mass and the spin of the remnant black hole from numerical relativity simulations. And there are fitting formula that are calibrated to a large number of numerical relativity simulations. So you can basically get a posterior distribution of the mass and the spin of the remnant black hole without looking at the part of the data that is produced by the remnant black hole. Then you can look at the part of the signal produced by the merger and the ring down of the remnant black holes, and make the same estimate of the mass and the spin of the remnant black hole. And so there is a bunch of ingredients have gone to these calculations. One is the template that I used to fit the data from the inspiral part as well as the post-inspiral part. And then the fitting formula that maps the initial parameters to the final parameters. So if all of these ingredients are consistent with the data or consistent with nature, then these two different estimates of the remnant black holes parameters has to be consistent. So this is what is shown from this right plot from the first binary black hole event. So the left plot, which is called the post-inspiral, labeled post-inspiral, is the posterior of the final black hole's mass and its dimensional spin estimated from the post-inspiral part of the data, while the right plot, which is a dashed line, which is labeled inspiral, is the same, estimated from the inspiral part of the data. And you can see that they're nicely overlapping. And interestingly, also, if the black contour shows the same parameters estimated using the full signal. So you can see that the parameters estimated from the full signal lies nicely between the intersection of these two different posteriors. So this shows that there is no inconsistency between the two parts of the data that we can relate using the assumption of GR. And one could also introduce some deviation parameters, which are the difference between the two different estimates of the mass and the spin of the remnant black hole. This is called the delta MF by MF. We can normalize this appropriately so that they are two-dimensional parameters. The x-axis shows the difference in the fractional difference in the two different estimates of the mass of the remnant black hole, and the y-axis shows the fractional difference in the spin, the two different estimates of the spin of the remnant black hole. And in GR, this has to be 0 and 0, which is shown by the black plus. And each of these contours shows the posteriors of these parameters that we estimate from various binary black hole events that was observed during the first two observing runs. And you can, if you make an assumption that this fractional difference between these two different estimates are independent of the intrinsic parameters of the binaries, like its masses and spins, etc., which is a strong assumption, then you can combine these likelihoods from multiple events to constrain these deviations better. And that is shown by these the gray filled region. So you can see that the combined posterior is much better constrained than the individual posteriors. And you can improve these constraints by combining these posteriors from many more events that LIGO and Virgo have observed during the third observing run also, which is being written up. And there are, this is of course not a very satisfactory way of doing it. I'll mention a couple of caveats in a minute. Ideally, what we should do is to look at if you have a long enough observation that has a sufficiently large signal-to-noise ratio, you can estimate the parameters of the binary from the early inspiral part, where the post-Newtonian description is known to be very good, and we expect whatever deviation that nature has from GR may not be very strong at the very early inspiral because it still samples a weakly relativistic regime. And if you're able to estimate the binary parameters in the very early inspiral, and if you're able to make a prediction of the final state, and if you are able to make similarly an estimate of the mass and the spin of the remnant black hole purely from the quasi-normal modes, as Vito Cardoso described yesterday, then this would be a much stronger consistency test. And currently we are unable to do it because of the lack of sufficient signal-to-noise ratio in the early inspiral and the very late ring down of these signals. But once we have such golden binaries, then we will be able to do such much stronger tests. And one could do many more interesting things. One is this idea that Miriam Calvero and et al. Proposed, which probably will be, Badri will be talking about this in more detail later today, is to test the black hole's area increase theorem. And there is a plot that they have produced, which is not purely from the observation, but is sort of an expected constraints on the area increase that you can measure from a binary black hole system, which is typical to the one, which is similar to the ones that LIGO has observed for the very first time, using upcoming observation runs using design sensitivity. So that is this dashed plot. So one could do some very interesting tests using future observations. Another idea is that because you can measure the mass of the total mass of binary from the early inspiral, and similarly from the remnant mass of the black hole from the late quasi-normal modes, one could calculate the energy loss due to gravitational waves, and we could test whether that energy loss is consistent with the prediction of Einstein's theory. If, for example, there are extra dimensions, etc., one could imagine some of the energy being leaked to these extra dimensions, and such energy loss, etc., would show up in this way of consistency test of measuring the masses of the early inspiral and the mass of the remnant black hole from the late quasi-normal modes. This is something that Arun described in detail yesterday, but let me just very quickly go through this. So one could also look at the inspiral part of the data, which is very well described by the post-Newtonian expansion in general relativity. And we know that the post-Newtonian waveform coefficients at each order is a unique function of the intrinsic parameters of the binary. For example, in the case of simplest case, the two masses of the binaries. So that is, for example, shown in the ith post-Newtonian order, or I by 2 post-Newtonian order. The coefficient is described by Pi, which is a unique function of M1 and M2. Now you can introduce an extra parameter. So you perturb the waveform by replacing Pi by some 1 plus delta Pi, where the Pi is still a function of the same unique function of M1 and M2, but you introduce an extra parameter delta Pi at each order also. Then you fit the data simultaneously with M1, M2 as well as delta Pi, so that if the data is consistent with GR, we should get a value of Pi or delta Pi that is consistent with 0. So the GR limit is recovered when delta Pi is 0. And one could estimate these posterior distributions of these parameters. And so far, so this shows, for example, the posterior distributions of various deviation parameters at various post-Newtonian order. Here, this is labeled delta phi n, but it is the same as the delta pi hat at various orders. And you can see that this violin plot shows the the posterior support at various values of these delta phi n or delta pi. And for example, the wider the violin is, the larger the posterior support. And you can, and these horizontal line shows the 90% lower and upper bounds on these posteriors. And you can see that these posteriors seem to be consistent with 0, which means that the data is still consistent with the predictions of GR. So and you can put bounds on these various deviation parameters. You can, and this Arun described it extensively yesterday. And the interpretation of these deviation parameters to the specific context of alternative theories is not very easy, because as both Arun and Victor discussed yesterday, one would expect that a true deviation from GR would manifest at multiple post-Newtonian orders, which would cause multiple post-Newtonian coefficients to deviate from their predicted value in GR. But due to the large correlations between different post-Newtonian coefficients that Arun described yesterday, currently we are unable to measure all of these parameters simultaneously. So what we do is to fix all parameters except one and constrain the deviations. So in some sense, it's some kind of an effective deviation that you see in one PN parameters, and it is not always easy to translate this to a specific bounds on a specific alternative theory. But in certain contexts, one might be able to do that. For example, in the case of the propagation effects of a massive graviton, one could show that those propagation effects only appear at a particular post-Newtonian order. So the deviation parameter in that particular order can be interpreted as a bound on the mass of the graviton, if only one considers the propagation effects, again, neglecting the generation effects. So there are several caveats in these such interpretation, but some interpretation is still possible. While these parameterized post-Newtonian deviations effectively capture effects of deviations in the generation as well as propagation of gravitational waves, one could specifically look at the propagation effects of gravitational waves, and again come up with some phenomenological description that deviates from the predicted dispersion relation that is in GR. So one such phenomenological modification is that you add an extra phenomenological coefficient A alpha to the GR dispersion relation, and so that is sort of A alpha, P to the power alpha, and C to the power alpha, and you can constrain these A alpha, this coefficient that adds this correction to the GR dispersion relation at various values of alpha. It's again a phenomenological descriptions, and you can, the absence of any such dispersion in the data, you can constrain the value of alpha for various values of, various A alphas for various values of alpha. And that is shown in this right plot here. This shows the bound on various A alphas as a function of alpha by combining a few binary black hole candidates that we have observed so far, which is from the O1 and O2. Just like in the case of these parameterized post-Newtonian tests, one could interpret bounds on various alpha in the context of certain theories. For example, if you put alpha equal to 0 and restrict A to be greater than 0, that would give the propagation effect of a massive graviton theory. And currently using such lack of evidence of dispersion or the upper bound on this alpha can be translated into an upper bound on the mass of the graviton, and currently it's of the order bounded to be less than of the order of 10 to the minus 23 electron volts. Similarly, alpha of some other values like 2.5, 3, etc., correspond to specific other alternative theories also. Are there any questions on this? Should I stop? Or go ahead.
Ajit, I have a question on your previous slide about A alpha.
Yeah.
So if you bring in this coefficient to the dispersion, this should also show up in the PN coefficients, right? Like, so even the -1 PN coefficient, can they be written in terms of these A alphas?
That's right. They would show up in the PN coefficients, and they would be a subset of the fully generic deviations that you write here.
Okay.
So this is slightly more restrictive than the more generic parameterized deviations that was written down here.
Okay, thanks.
Ajit?
Yeah.
Here. So, okay, so when you write this theory with a massive graviton, this is just a propagation, right?
That's correct, yeah.
So you, do you know anything about how these waves will be produced in massive graviton theory?
No. That's a very strong assumption that you're putting. But I think I've heard people making some arguments that because the curvature scale of the source is so small as compared to the scale of propagation, one could argue that the final effect would be dominated by the propagation effects. I think it's just a hand-wavy argument. I don't know how rigorously it can be quantified.
Okay, because massive graviton theories will have their own pathologies.
That's right, yes, yeah.
But you're just considering the propagation part.
That's correct, yeah. There is no way, so no one has, as far as I know, no one has successfully generated gravitational waves from a massive graviton theory.
Okay. Ajit, are you saying that graviton will have a non-zero mass by this constraint?
No. We are so far the gravitation observations are fully consistent with graviton being a massless particle. So what we are putting is we can put an upper limit on the possible mass of graviton. It has to be less than 10 to the minus 23 eV by c square, but it can very well be 0.
Agree. Like it will exist unless you prove that graviton has a zero mass.
That's right. Yeah.
Okay.
Yeah. So we are slowly bounding. We are putting stronger and stronger upper limits on the mass of the graviton.
Just a comment. So recently, here with students here, we have obtained updated limits on graviton mass using clusters. So I guess just one comment. So when I looked at the LIGO detection paper, right, there was one statement which made me jump off from my chair, which is that the limits on graviton, again, this is not related to gravitational waves, but the latest limit on graviton mass from clusters was from 1974. Okay. And this is a paper which is cited only by gravitational wave people, not by cosmologists or galaxy clusters. So been shocked by that. I think I did some work with students to update the limits, and I think with the clusters we get up to the order of 10 to the minus 31 eV. I think group at Delhi University has also done that. So that's just an aside.
Yeah, thank you, Shantanu, for pointing us our ignorance. Certainly, this is something.
Yeah. And just one more thing, in the LIGO main detection paper, right? The wrong reference has been cited. I think the best limit from weak lensing is by a group from Chaudhary et al. At Delhi universities. But I think instead they cited Shayant and Chaudhary, who was actually a postdoc at Ayuka. But in the test of GR paper, the correct paper is cited. So serendipitously, Shayantan got a lot more, I think, citation or this thing, whatever, anyhow.
Okay, thanks for finding this out. I'll maybe write to you after this talk to get the right references. One thing so when I looked at this literature sometime back, just almost 10 years ago, was that I had the impression that the constraints from the clusters are highly model dependent. Has this changed?
So you see any modified, yeah, so there's nothing is, yeah, surely it is, assumptions are being made, certain assumptions have been made, because I guess the work which we did, we assumed that both dark matter and ordinary matter have both dark matter and ordinary matter sort of experience Yukawa potential. Now, you could argue that maybe only dark matter obeys Yukawa potential, and since we don't know dark matter, what dark matter is, there is a little bit of caveat related to that. So yeah, so I think any limit on graviton mass has some model dependence built in. I think as I just came in, I think there was some discussion, even the LIGO, this thing as I think there was also a paper by Stanley Deser on this, that so far no one has been able to generate gravitational waves in a massive gravity. Okay, so so in some sense, so the one word answer is yes. Okay, but I think the limits which we have done are much more refined compared to the very crude limit by Goldhaber. So what by Goldhaber and Nito, which is what is usually cited in Cliff Will's papers. Okay, so that limit, I think all they have done is invoke Bertrand's theorem. Okay, which you can find in Goldstein's book. In fact, there also they don't make any assumptions about dynamical mass. Okay, so whereas we have made, we have also have a confidence level. Okay, unlike the Goldhaber Nito limit. So I don't know if that answers your question.
Yeah, I understand. So yeah, I will look at your paper carefully after this, but thanks. Okay, so any further comments or questions on this part? Okay, let me go ahead. So let me slightly switch gears now. So most of these bounds that I was talking about so far are are derived from fairly sophisticated inference on the data. But a single observation, a very simple observation that was made possible by the binary neutron star system that was observed in 2017 had enabled us to measure the speed of gravitational waves, which had a lot of impact on alternative theories, especially in the context of cosmology, etc. So the story is the following. For this binary neutron star merger, which is codenamed GW170817, we observed LIGO and Virgo observed gravitational waves from the inspiral of the two neutron stars. And within a second or so, 1.7 seconds after the expected merger, the Fermi satellite observed a weak gamma ray burst also. And the fact, and this system was estimated to be at about 40 megaparsec. So the fact that we have observed both gamma rays as well as gravitational waves with a time delay of the order of a second has put a very strong constraint on the relative speed of gravitational waves. And the relative speed of gravitational waves is now constrained to be within a fraction of 10 to the minus 15 to the speed of light. And this has enabled a lot of interesting tests of equivalence principle and Lorentz violation in the gravity sector, etc. And this, I understand, although I'm not an expert on this, is also that this constraint on the speed of or gravitational waves has now ruled out or heavily constrained several alternative theories that are invoked in the context of cosmology, which is used to explain the accelerated expansion of the universe, etc. So I also am aware of that. Certainly, I'm not an expert on this field, and I'm also aware of that several people are now finding ways of bringing them back by introducing several other things. But it seems to have a very strong impact in ruling out and constraining several alternative theories. Another interesting test of the gravitational propagation can be done by comparing the luminosity distance to this binary neutron star merger that was estimated from gravitational waves as well as electromagnetic observations. So the story is the following. The gravitational wave, the compact binaries are standard candles, so they can be described accurately using a small number of parameters like the masses of the system, etc. And from the frequency evolution of the signal is completely given by the intrinsic parameters of the system, such as two masses of the two objects. And if you are able to measure the intrinsic parameters for the frequency evolution of the signal, you can calculate the absolute amplitude or absolute luminosity, and you can measure the intrinsic amplitude, and you can measure the apparent amplitude or apparent luminosity from the data, and the ratio of this gives you a measurement of the luminosity distance. So in that sense, gravitational waves are standard sirens, which are analogous to standard candles, not even standardizable. They are absolutely standard candles. And using gravitational waves, we can measure the distance to this binary neutron star object that was merger, that was found to be about 40 megaparsec with fairly large error bars. And using electromagnetic observations, the host galaxy of this system was also localized. And there was an independent estimate of the luminosity distance to this galaxy using the Tully-Fisher relationship. And this two independent measurements of the same quantity, the luminosity distance, allowed us, or people, to constrain the number of non-compact extra dimensions. So the idea here is that if non-compact extra dimensions exist, gravitational waves could leak into them, and hence some energy would be lost, and the luminosity distance that we estimate from the gravitational waves would be larger than the luminosity that you would estimate from the electromagnetic waves. Because in this scenario, the electromagnetic waves are not supposed to leak into extra dimensions. Only gravity couples to this extra dimensions. And because of this energy loss, the gravitational wave would appear to be weaker, and hence you would estimate a longer, farther distance. And the fact that these two estimated distances are consistent with each other has enabled people to constrain the number of non-compact extra dimensions. There's a posterior on this D parameter, which is the number of extra dimensions and number of dimensions or spatial dimensions, and that is consistent with being 4. You can introduce a more sophisticated model. This is again a phenomenological model, and constrain the parameters, which LIGO collaboration has done also. Another way of
can I mention one more test? I apologize if it was mentioned earlier. So when you mentioned velocity, this thing, right, that I'm guessing you refer to the vacuum speed of gravitational waves. Just from you, one more important point is that we also know that the matter-dependent velocity, Shapiro-Delia of gravitational waves, is same as that of photons, and that rules out, I guess, relativistic Mond theory. I think we wrote a paper on that also. So that's, but that's an independent. So that's, I guess, a different observable than what you were mentioning.
That's right. Yes, I weakly mentioned this equivalence principle test, but I intended to refer to the Shapiro-Delia measurements also. Yes, thank you. Another probe of that one could do using gravitational waves is the nature of gravitational waves themselves, akin to the speed of gravitational waves. So, for example, we know that in GR, gravitational waves admit two linearly independent polarization modes, which are tensor modes. They're typically called the plus and the cross polarizations. So, for example, these shows the left two plots shows the deformation that a ring of test particles would undergo when a gravitational wave go perpendicular to this direction of the screen, so the Z direction. So you would see this ring to be deformed into an ellipse in one direction, and the next half cycle, this ellipse would be deformed in the orthogonal direction. And the other polarization mode also does the same thing, except that the orientation is shifted by an angle of 45 degrees. So these are a quadrupole nature. But a generic metric theory of gravity can allow up to 6 polarization modes, 2 vector modes, like shown in the middle pictures, where the wave is traveling in the Z direction, and you see a longitudinal component also in this vector deviations, and a scalar mode, which is shown in the rightmost plots, which could be either a transverse mode, which is called a breathing mode, which is shown in the top plot, where the circle expands and contracts, or a longitudinal mode, where the wave is propagating in the Z direction, and you see a longitudinal deviation also. And in principle, the nature of the polarization can be measured using a network of detectors. And the idea here is that each detector, each quadrupole detector, would measure one linear combination of the two polarizations. And if you have, in principle, if you have 6 linearly independent detectors, you could, in principle, extract the 6 polarization modes. But in practice, it turns out that these 2 scalar modes are completely degenerate. So one could only measure a combination of these polarization modes, and one would need something like 6 linearly independent detectors. And currently, we have only 3 detectors, and even the 2 LIGO detectors have very similar orientations by design. And thus, it is not possible to extract these polarization content from these observations. But one could do something very simple. So there's some very simple models have been tested against. So one here, the idea is that you can check whether a pure scalar only mode is preferred over a pure tensor only mode, or a pure vector mode is preferred over the tensor modes. And here also one need to make some specific assumptions of the time evolution of the signal, or the phase evolution of the signal. And here it is done assuming that these vector modes as well as the scalar modes follow the same phase evolution as the tensor modes. And using such simple models, we have concluded that the tensor mode is preferred over the pure scalar mode or pure vector mode. Which is not a very sophisticated test, but this is the one thing what one could do right now. One could do similar test using continuous gravitational waves from spinning neutron stars, because these neutron stars, if you are able to observe them, they would shine continuously, and you could observe the signal for months or even years, and during which the Earth would rotate and move around the sun, and one would measure different combinations of the same polarizations, and one is able to extract polarization content much more than these transient signals like the compact binary mergers. One could also get some measurements from the stochastic background if one is able to measure this also. But the detection rates for both the spinning neutron stars as well as the stochastic background is currently very uncertain. So the only thing that we know that are guaranteed are the signals from the compact binary coalescence, which we know that we will observe hundreds of them in the next few years. So to do such tests using more sophisticated tests of the polarizations using compact binaries, one would need at least 5 detectors. So the fact that the Kagra and LIGO India are expected to contribute to this, to join the international network of gravitational wave detectors in the next several years, it gives us a hope that we will be able to do such tests after the next few years. Another intriguing possibility that we have explored recently is to see if strongly lensed gravitational wave signals would allow us to put better constraints on the polarization content. So here the idea is that recent estimates, assuming GR and standard astrophysics, predict that something like a small fraction, like a 0.1% to 0.5% of the binary black hole that we would see in the next several years would be strongly lensed by intervening galaxies, and possibly clusters of galaxies also, which means that it would produce strong lensing, and you can get multiple images or multiple copies of the same signals with time delays of several minutes to several weeks, and it could go to several months if you assume cluster lensing. And the Earth would have rotated in between, so you would, in these 2 copies of the same polarizations, you would observe 2 different combinations of the same polarization because the Earth would have rotated. And essentially, such an observations would double or multiply the effective number of detectors to observe the same source. And one could, in principle, extract the polarization content much more accurately than using a single observation. And here the assumption, which is very strongly likely to be true, is that the lensing does not affect the polarization content, because one could show that lensing does parallel transport the polarization vectors. Polarization tensors, sorry. And this shows is a plot from an upcoming work by one of our students, Srishti Goyal. She shows that how the model selection of different polarization models can be improved significantly from strongly lensed sources. Another interesting, so most of these tests that I've talked about are on the nature of the theory of gravity. The gravitational observations also allow us to probe the nature of compact objects, which was discussed in detail by Victor yesterday, so I will not spend a lot of time. And one such idea is the evidence of quasi-normal modes. And so here is the idea that the late stages of the post-merger signal from a binary black hole coalescence should be well described by a spectrum of quasi-normal modes. So this shows a comparison of a numerical relativity waveform, which is shown in the black, which is the late part of the binary black hole merger, and its comparison against the dominant quasi-normal mode from a remnant black hole of the appropriate mass and spin. So you can see that the late part of this ring down is very well described by a single, just least damped quasi-normal mode. And the data following the peak of the very first binary black hole event, 150914, is consistent with the presence of the least damped quasi-normal mode, which is inferred from the the mass and the spin of the remnant black hole. This is a plot that Victor discussed in detail yesterday, so I don't want to repeat the same statement again. So the summary is that the late part of the data is consistent with the presence of the least damped quasi-normal mode for a Kerr black hole of appropriate final mass and spin, but one cannot rule out the presence of additional quasi-normal modes also. Like one could fit the same data using some other higher modes also. So it is not conclusive. However, there is recent work. This is a work by Max Sissi and collaborators, including Tukolsky and so on, which claim that if you include the overtones of the same least damped quasi-normal mode, which are shown by this n quantum number, then it turns out that a longer part of these final ring down can be fit by the least damped quasi-normal mode itself, and they claim a much more confident detection of the presence of the least damped quasi-normal mode, and this is a plot that they have in their paper. Anyway, certainly in the future, with observations of large signal-to-noise ratio, one will be able to measure many different quasi-normal modes, and as was very nicely illustrated by Vito Cardo's slide yesterday, one could make the measurement of the mass and spin of the remnant black hole from different oscillation modes, different strings in this picture, and one could do very nice consistency tests. And I believe that this is an area of active research, and I would assume that Bedri would talk in more detail about this frontier in his lecture later today. Again, this is another idea that Victor discussed in detail. What would happen if you replace the black hole horizon by some partially outgoing boundary condition, which is the presence of an extra compact object, which is more compact than the horizon, the light ring of the corresponding black hole. So what you would see is that instead of a purely ingoing boundary condition, you get a partially reflecting boundary condition, and modes of the radiation would be trapped between the light ring and this other boundary condition, other boundary, and would get periodically reflected, and you would see echoes after the post-merger signal. This is an interesting prediction of the presence of or the absence of horizons in this compact object. And several groups have looked at this in LIGO data, and there are conflicting claims. One group has claimed a tentative evidence in the LIGO data of the presence of such echoes using a phenomenological model. And this is not very significant. The significance is of the order of 2.5 sigma, which I think is now broadly agreed upon by other groups also, who also claim. But the question is, there are two questions. One is that whether this 2.5 sigma is sufficient to claim an extraordinary detection, extraordinary claim. And also, it turns out that when you look at the significance as well as the echo parameters from many different binary black holes as well as the neutron stars, if you want to explain all of those simultaneously, it turns out, that is my reading, that you need fairly contrived models of these echoes, which is, but anyway, this is an interesting area of research, and we need to wait for future observations and theoretical developments to see any conclusive evidence in this frontier. Another signature of the exotic compact objects is again also described by Arun and Vito yesterday. There could be, and also there could be evidence of the tidal deformation of these objects, and we do not see, if this object is a black hole, we do not see any evidence of tidal deformation in the gravitational field. But if the object is not a black hole, such an effect of tidal deformation can be seen in the gravitational waveform, which can be characterized by leading order by a single parameter, which is called the tidal deformability, the lambda, which relates the induced quadrupole moment Qij by the tidal field epsilon ij. And people have, there are methods proposed to use the obtained upper limits on the tidal deformation. So far, all the binary black holes show no evidence of tidal deformation, although it's not published work yet. And such upper limit on the tidal deformation can be translated into constraints on the equation of state of such extra compact objects, if they can be thought as the reason for these binary black hole like gravitational waves. Another idea is again described by Arun yesterday, is to look at the signatures of the spin-induced quadrupole moment or other multipole moments. One could use the measured values of these to constrain the nature of these objects. Another idea that was described in Sukant Bose's talk yesterday was to look at the signature of the tidal heating. So there are different observational signatures of compact objects other than black holes has been proposed, and there are interesting searches ongoing on the existing LIGO Virgo data. But so far, there has not been any significant evidence of the presence of black holes other than objects other than black holes in the data yet. So let me conclude in the next couple of slides by making some conjectures for the near future, mostly from the observational side, because we have heard some really excellent theory talks yesterday, and we'll hear more about the theoretical explorations in the later talk today also. One is that in the near future, LIGO and Virgo, along with other observatories like Kagra and LIGO India, which are expected to join the network in the next several years, are guaranteed to detect hundreds of compact binary mergers in the next few years. And this could even go to a couple of thousands, depending on the uncertainties in the event rate and the detector's progress. And this would allow us to produce significant tight constraints on deviation from GR, as well as deviation from the black holes in GR. This could either be done by combining multiple constraints from multiple events, or from a handful of golden events, with very high signal-to-noise ratio. And note that while they are dominated by the statistical errors, the precision of our observations, these, the statistical errors will be significantly reduced by these two means I mentioned in the second bullet, and this will enable us to do precision tests in the next few years. And the right plot shows the expected number of detections that LIGO and Virgo are expected to see in the next few years. And the O3 is already over. The vertical axis is the mean number, the expected number of detections per year, and the horizontal axis is the observable time frequency volume, is normalized to the time frequency volume of O1, the first observing run. And with better detectors, we would improve our horizon and would improve our spatial volume. And with longer observing runs, we would increase our space-time volume. And this curve, this line would just go up and can hit several hundreds and several thousands in the next few years. So coming back to this will allow us to improve the statistical precision of constraints. But precision does not mean accuracy. So this means that our error budget will be dominated by systematic errors, which is what is undergoing in cosmology these days. So it is an area of precision cosmological measurements, and we have multiple measurements of the same cosmological quantities, most famously the Hubble constant, which are thought to be very precise, but multiple observations don't agree. So most likely explanation, unlike there is some exotic physics ongoing, is that there is some unknown systematics in one of the observations or both of the observations, which we are unable to account for. And it is very, very likely that the gravitational wave observations would reach in this regime in the next few years. And it is very important from an observing front to understand the systematic errors. These systematic errors basically come from the incomplete understanding of the data, which could be from the signal model as well as the noise model. And this can be very easily confused with a deviation from GR. So it could be a false alarm. So let me, I thought of like three main sources of such systematic errors. And one is the incomplete modeling of the expected signals in GR itself. For example, we know that our signal models currently do not include all possible effects that are allowed in GR itself. For example, the effect of the black hole spins misaligned, which cause the precession of the spins as well as the orbit, which is not taken into account in complete accuracy in the current waveform models. We do not include all the relevant higher modes of the radiation, non-quadrupole modes of the radiation yet, although there is significant progress in this front. There could be, the standard paradigm is that due to the long inspiral of the binary black holes or binary systems, by the time they reach the frequency band of LIGO and Virgo, the orbital eccentricity would be negligible because the radiation reaction effects. But there could be some small residual eccentricity, especially if these binaries are formed at close separations in dynamical environments. So this could, if you do not account for this, this can cause biases in our inferred parameters. There could be effect of internal structure of the compact objects like neutron star, which would appear as higher order post-Newtonian terms. There can, in general, be issues of numerical accuracy from numerically waveforms, or missing higher order post-Newtonian terms in the post-Newtonian expansion, etc. So in general, incomplete modeling of the signals in GR could manifest as a possible violation of GR. There are equally big challenges in understanding noise. We approximate the noise to be Gaussian, which is true to a good extent, but we know that there are non-Gaussian trails in the data, which are produced by glitches and other non-stationarity in the data. There are slow deviations from the stationarity of the data, so typically called the drifts in the power spectral density estimates. And now groups outside the LIGO has found that if you properly account these drifts in the PSD, one could uncover more sub-threshold candidates from the LIGO data, etc. There are issues of detector calibration, which is still uncertain by a factor of a few percent. And these could, in principle, be manifested as deviation of GR. There are also interesting possible astrophysical effects. And one possible effect is the gravitational lensing of the gravitational waves that are caused by objects between the source and observer. In particular, if the objects, this lens gravitational radius is comparable to the wavelength of gravitational waves, there can be wave optics effects which would deform the waveform. This is a possible source of the deviation GR, pure GR waveform. There can be matter effects in the environment if there are accretion disks, etc., sufficiently close. This was mentioned in Vito's talk yesterday. There could be external gravitational effects from external bodies, for example, a third body in a hierarchical triple, which would modulate the waveform in a subtle way. So one could think of several such astrophysical effects also. And people have started addressing these questions one by one. So there was we saw a very nice summary of the various astrophysical effects in the calculation of the quasi-normal mode frequencies in Vito's talk yesterday. There has been investigations of the effect of the higher order modes, and slowly there are such calculations coming up that quantify the effect of various systematic errors, various sources of systematic errors. So let me stop here by giving you a quick summary. So we know that the gravitational wave observations have now enabled the first test of GR in the highly relativistic strong field regime. And in the absence of accurate theoretical predictions in alternative theories, the current tests only probe the consistency of the data with GR. So these are sort of the class of null tests. And we expect a considerable reduction in the statistical errors, which currently dominate the error budget in the next few years. And this could either be coming from the observation of a small number of golden events, or by combining several observations. And soon we'll reach a regime where the error budget is dominated by systematic errors, and we will have to prepare for this along with other progress in the theoretical frontier. So let me stop here, and thank you very much.
Thanks a lot. Thanks a lot, Ajith, for this wonderful talk. So the floor is now open for questions. Please go ahead and ask.
Thank you.
Yeah, Ajith, it's Arun here. Can you go to the slide where you showed the Srishti's result for the lensing based polarization constraints?
Yes. Yeah, this one. Yeah.
Yeah. So can you quickly explain the figure once again? Then I have a question, but I just wanted to understand. I couldn't appreciate it. Just
right. So this is basically the distribution of the base factor. So what you do is you have simulated a population of binary black holes according to some realistic astrophysical situation, and assuming GR also. They are basically tensor only polarization modes.
Yeah.
And then we compute the base factors and the likelihood ratio between two models. One is that the waveforms are only tensor modes, and another is that they could be vector modes or scalar modes. So this is the horizontal axis is the distribution of the base factors between these two competing models. So
okay.
If base factor greater than 1 means the right hypothesis is recovered.
Okay.
Right. This is log base factor. So 0 greater than 0 means the right hypothesis is recovered. Now this thin line shows the expected distribution if you just look at unlensed events of similar strength, the thin, for example, thin red line. But if you have two events that are lensed of similar strength, that base factor is increased.
Yeah.
So what we remember that now for 50% of the events, the base factor is increased by more than a factor of several.
Okay. Yeah. Yeah, so I mean, I just wondering. So, of course, this is one way of testing. If you have 5 detectors, we can of course have a polarization test either by null stream or even doing a proper parameter estimation. So, of course, I can see that this very there are aspects which are complementary to this. So, I'm just wondering how would is it is this is the expected bounds on the alternative polarization, can it be compared using any figures of merit with the other methods, or it's
Yeah, that's a good question. I think let me just clarify that this is entirely assuming only 3 detectors.
okay.
So with lensing, your 3 detector will become an effective 6 detect network.
Yeah,
and if you have a 5 detect network, with lensing, that would become effectively a 10 detector network.
Yeah.
So that lensing always improves this
Correct,
thing.
yeah.
But now you can do this in multiple ways. This is a model dependent way. One could also do this in a model independent way using null stream and other waveform independent reconstructions. And there is work going on by multiple groups, including so a student of Alan Weinstein at Caltech, and who looks at this. We also intend to look at this, but I don't have there is the results on this that is obviously out. But I would imagine that if you assume models, then the constraints can be better.
Yeah.
But of course, model independent constraints are more robust.
Yeah. Okay, fine, thanks.
Can I ask a question?
Sure.
Yeah. Can I ask a very general question? Is the quasi-normal mode structure almost the same as what Visheshwara had predicted, or has it changed due to corrections or precision calculations?
So the leading, the structure of the quasi-normal modes hasn't changed. So what people have done with more accurate calculations is to calculate the quasi-normal mode frequencies more precisely as a function of the black hole parameters. Is that a fair summary, Sudipta?
Yeah, of course.
Okay, thank you.
So there is one question, a few questions in the chat, Ajith. So there is a question from Abhishek Hegre. It says
so
that you can see it, right?
Yeah, right. Is the first order approximation for tidal response mentioned in the talk good enough for modeling the waveform near merger, or does LIGO use numerical waveforms to infer the estimates of tidal parameters? This is a very good question. It is not. So the first order approximation, it is done in the adiabatic regime. So it is valid only in spiral only, and in particular in the early in spiral only. But so that means that whatever inference that we need to make from the data, you have to look only, you have to make it only from the in spiral part of the observed signal. So you have to basically truncate. You have to throw away the data that is close to the merger, etc. But for the case of neutron stars, this is actually happened to be good enough. The reason is that the late in spiral and the merger, etc., of the neutron star binaries happen to fall in the high frequency band, so where the LIGO is not sensitive to. That's why, for example, for the measurement of the equation of state, etc., one is just using post-Newtonian spiral waveform. Just calibrate a little bit to the NR at latent spiral to extract the tidal deformation terms. But I guess now we are talking about the case of massive objects, where the merger also happens to be in the LIGO frequency band. So to do that, since we don't have a good model of the tidal deformation and the tidal effects near the merger, we will have to artificially truncate the data at the end of the inspiral, where we expect or hope that this description, this adiabatic description of tidal deformation is valid, and then only make inference from that small part of the inspiral part of the data, which would make our inference less precise, but hopefully will not introduce any systematic biases.
There's another question from Surajit. In the second slide, while considering the conditional probability.
Okay, while considering conditional probability, it seems that null hypothesis is treated as a condition as the conditional event. How can it be? How to interpret type 1 analysis? Okay, so the type 1 error is so the brute force way of estimating the type 1 error, which is the false alarm probability, is you estimate the detection statistic from pure noise, and then you get a distribution of the detection statistic that you estimate from pure noise. So that is it is in that sense that I said that it is a conditional distribution of the detection statistic under the null hypothesis. Then you can ask the question, how often does this detection statistic cross a threshold? And that gives you the type 1 error, false alarm probability. Now, how do you get the type 2 error or the detection or the false dismissal probability? You will have to simulate a population of the signal that you're going to detect and look at the distribution of the signal to noise ratio in that you estimate from those simulations or those injections. And you can ask, how often does the derived statistic take a value less than the threshold? That gives the false dismissal probability. In LIGO, both of these errors are estimated in a brute force way by doing a lot of simulations in the data, by injecting fake waveform into the data of LIGO.
If there is any other question, you can ask. We have time.
Hi, Ajith, Arif here.
Hi, Arif, yes.
Can you go back to the slide where you showed the IMR city posterior?
This one? Is it this one, Arif?
Yes. So in the delta and posterior, yes. So in the delta and posterior, I can see that there is one event which is picked slightly, I mean, away from 0. Is there any reason?
Yeah, so these are things that I alluded to in the discussion of the noise artifacts. So this was investigated, and our best conclusion is that there is some small non-stationary transient in a part of the signal.
Okay,
that causes a large support for the posteriors at non-GR values, but it is still within the 90% confidence region of GR. But we would see more and more of such events if we do not understand the data well enough, or it's probably very hard to understand the full data anyway. So you need to at least quantify how often we expect such noise-induced, deep fake deviations in our data.
Okay, can you go to the previous slide?
This one?
Yes. So in this plot, so with respect to the IMR contour, I can see the inspiral contour is slightly shift towards the higher mass, right? And
so these are due to the inherent correlations between the parameters.
For post-inspiral, it's slightly
yeah. These are due to the inherent correlations between parameters in the data. So in the signal. So for example, we know that if you look at the early part of the inspiral, right, the M1, M2 is correlated in such a way that the chirp mass is the best estimated combination of parameters. So if you draw, for example, a correlation ellipse in M1, M2, it has a particular orientation. But if you look at the late part of the signal is determined by the final mass of the black hole. So that should be the best estimated parameter, the total mass. So the orientation of the correlation ellipse would change as we progress through the waveform. So this is because your statistical errors are determined by basically the correlation of these parameters, and the correlation of the parameters or your covariance metrics in that sense has different orientations from in the late part of the signal and the early part of the signal.
Okay, thanks. Thanks a lot.
Any other question?
Yes, I have a question. Hi, Ajith, this is Ajith from Ilawa.
Hi, Sujit, yes.
Hi. So I have a naive question. So I was wondering, like we are detecting this GW in our Earth-based detectors, and then also locating the sources from where it has been originated. So in this process, from the source to the detector, it may have gone through some objects or I mean some clusters or stars or galaxies through which it can get length. So those gravitational waves also may deviate. So can we also detect some signatures of those objects? Because I mean we don't know that the entire path, or it has all I mean in the detection process already these things are being taken care of. I don't know. I mean
yeah, that's a very good question. Yeah, that's a very good question, and that's an active area of research in gravitational astronomy these days, the lensing of gravitational waves. And there can be multiple sort of signatures of such lensing effects. One is that if these lenses are like galaxies or clusters, the lensing happens purely in the geometric optics regime. So it would not deform the waveform in any way, any significant way at least. So the only signature of the lensing that you can detect is by, but such strong lensing can produce multiple copies of the same signal that are separated by minutes to weeks. So one signature of such lensing is by identifying waveforms of same shape in the data, just separated by minutes to days or weeks. So that's one way of detecting lensing signatures in the data. But now, if you think of much more small lenses like stars or compact objects or black holes, etc., whose gravitational radii are comparable to the wavelength of gravitational waves, lensing could also introduce other wave optics effects like diffraction, interference, and so on. And then that would deform the waveform in a characteristic way. And if you have a point mass lens, that the deformation can be computed very easily. And people have looked at we also have looked at the effect of such lensing deformations in the data. And so far we have not seen any. But that is going to be a very interesting probe in the next several years. And that's a very active area of research now.
Just let me add, I mean, as Ajith also mentioned, and I alluded to, they also experience Shapiro delay, even though in principle it can never be absolutely detected, but that's also, it's there.
That's right.
Great. Any other question?
Ajith, I have one question, Aditya.
Yes. Please.
So while you were explaining Arif why the contours of the inspiral part and the post-inspiral part in the IMR consistency is different, you told that it is also because how the masses are correlated, how they come up in that phase of the signal. So say for Lisa band, where we if correct me if I'm wrong, but in that frequency, in the Lisa frequency band, we will rather be seeing at the inspiral part of the signal, right? So these things will also come up there, like when we do parameter estimation with Lisa signals, then these kind of biases will also be there.
So this is not a bias. It's only how because the posterior is always consistent with the true value, right? Only that it has a shape that is different, depending on the part of the signal that you're measuring. The shape of the posterior or the likelihood can have different orientation, but they are always consistent with your true value. I mean, they can be in the absence of any biases.
Okay, so the peak is around the true value only. The peak peaks at the true value.
Yeah.
Okay, thanks.